Well, good evening, everybody, and I hope everybody's safe and sound. I'm sure that a lot of you are getting a lot of observing the last few nights. It's been crystal clear. Whoever expected April would look like this? And so let me show you a few things that have been happening since the last meeting. We've had quite a few things that have been going on in the sky. Of course, last time we met, we had the equinox on the 20th, and then on March 4th, this is part of the story. March 4th, there was a launch, another launch from SpaceX for the Starlink. Okay, this was the 8th time that he used this particular booster. They put 60 satellites in orbit. Pretty routine, right? Right? So just another one of those launches they did, and setting up all the satellites by design. Yeah, no big deal, no problem. Okay, the first days landed just fine, and what have you. Okay, nothing really came out of it. However, okay, with the Starlink, they're coming up with hundreds of these in satellite orbiting around the Earth. They're providing Wi-Fi to a very remote area. It's already been in service. Some I've been already getting reviews about these new satellite dish by Starlink and what have you. It's already, I don't know, somewhere in the 20, 30,000. They're getting up there pretty quickly. Okay? But then on March 25th at 9 p.m., for some reason my phone was just going crazy. Okay? At that very moment,
I am! What is that? Guys, it's beautiful! Oh my god, you can't even see it in the video! What is that?
there was videos and emails and
my
texts that
God.
were just non-stop about this particular fireball that was happening in the sky, and the media started calling me, and it said, my first reaction was, that's just way too slow for a fireball. It was reported everywhere, from Seattle to Canada, Idaho, Oregon, seeing this large fireball that lasted for about 15, 20 seconds. And so that was the first thing I checked to see if what's out there, because I didn't see it. But the phone was just going crazy to the point that I couldn't even respond. And then I got the text message from all people, Jonathan McDowell. He's a Harvard astronomer. And said, hey Jim, did you see that fireball? I didn't know Jonathan. But then when I went to his site, started to realize this guy knows how the information. Then he showed me the map. He's saying, Jim, this particular fireball you're seeing is actually debris from the stage 2, the Starlink. And the stage 2 failed to do orbit. And so what we're seeing is this, which is a very large rocket that was entering the Earth's atmosphere somewhere at 40, 60 miles, which started to make sense because it was moving fairly slow, moving from 17,500 miles per hour, moving into the atmosphere. If it were the fireball or bolide, it had been much quicker. Right? So my initial reaction was it was man-made. And then Jonathan said, no, this is stage 2 from the Starlink. Right? And then he used this website called Aerospace. Some of you may be familiar with this. Okay? And Starlink, he knew there was a candidate to fall back, but he had a span of 5 hours to know where it's going to fall. Okay? And so, if you're ever curious about where these things are, go to this website. And so he started following up and started showing these orbital map. He's saying, oh yeah, we saw it earlier, it's getting lower and lower in the orbit, okay? And then it finally entered the Earth's atmosphere, and the fallout occurred over Oregon, Washington, into Idaho, okay? And so he was my source for that night, and so I was able to pass on this information to the public. And then I got into the media to trying to explain what this is. There we go. Talking about the event, and they were helping us explaining what we were seeing in the sky. Now, according to Jonathan, this was the 14th time that a 1-ton object returned to Earth since January 1st. So if this says anything, this is the problem, right? But what's ironic is that SpaceX didn't have a communication director, wasn't really warning us about this, and it was just all kind of, well, why didn't they tell us? Okay? And so that was kind of the confusing part. People trying to get a hold of SpaceX, they weren't responding. Okay? So Jonathan knew pretty much, because that's what he teaches at Harvard. They talk about these kind of things, and talking about space junk is a big problem. Okay? And so then, around April 2nd, they did find a debris in central Washington, and it was confirmed that this is one of the parts from the SpaceX. Right? And so that was one of the first signs. Of course, people were asking, are we going to get any debris from this? And I said, well, we weren't expecting any. Okay? Because they're required to make these so that they would burn up in the upper atmosphere. But one did fall. But then later, they found something like this at Walpart. These are shrimp fishermen, and they saw something floating in the water, and they pulled it in. And of course, what did they do? They pulled it out, not realizing the hazard that could be associated with these debris. And so immediately they started calling me and said, what do you think, Jim? And I said, I can't confirm anything. And I had a contact at SpaceX to ask him, what did he think? And he won't answer that question. He won't say yes or no. So they brought in the police and the hazmat, all of that, and immediately they took it away because there's a potential hazard. That's one of the first things I said. You do not want to handle these things. You don't know what you'll be dealing with. So they took it away, some undisclosed location. But they never have confirmed or denied since that time whether or not it was indeed from the SpaceX, right? And I've been trying to get a hold of SpaceX. They said, thank you very much, Jim, for contacting us. Okay, that's it. Okay. And you go back to the website, these are actually upcoming events that where they're expecting these objects to fall back to Earth. Okay? And so you can see that one after another. Is this going to be a rare event? Well, sort of. But again, it's coming back to Starlink, and more Starlink. Okay? That says something. Okay? Right there. Right? And so finally, got a a Facebook message saying, now SpaceX is getting a communication director. Okay? And so maybe someday they'll be able to respond to the public question about these things and the launches and so on. So they finally recognized, oh, we better get a communication director for this. Right? And so that was the big event for March 25th, and people are still talking about it. Coming up, we have the pink moon on the 26th of April, and then we have just 3 years away from now, we have April 8th, which is going to be the part 2 of the Great Totality that are going to cross America. And this time it's going to be on the East Coast. And so this is going to be a 4-minute totality, 4 minutes and 26 seconds, so twice as long than what we had in 2017. Okay? Carbondale, Illinois, again, will be a central point for the totality. We're going to get here, there we go, we're going to get a 22%. Okay? Not exciting, but it's still technically an eclipse. And I know some of you are making plans to go down to Texas or Mexico and what have you to watch this totality in April. Okay? And then we just had the celebration of the 60th anniversary, okay, of the Gauguinian, there we go. And so that was the 60th anniversary for the first man into in space. It only lasts for 1 hour and 48 minutes. Right? And so one of the things that people have been asking me, where is that capsule now? It's on the Economic Center in Moscow. It's on display. That's where it ended up. Right? Then we had a return of Kate Rubins from the International Space Station. I believe she was up there for 300 days or something in that neighborhood. But she returned to Earth in good shape. It's pretty crowded up there now on the space station. They had 10 up there for a while. So it's been a real party up there on the space station. I have no idea where everybody's sleeping. But she returned to Earth. And I don't know if you guys know this, but she is one of the candidates to go to the moon. Okay? And so I would have a good guess that she could be the one that's going to be going to the moon. Okay? And then we have Perseverance. Okay? Everybody's talking about Perseverance. And they took this wonderful shot of a selfie between Perseverance and Ingenuity. And this has just turned out to be one of my all-time favorite pictures from Mars. This is just a fantastic photo. The rover and the small little helicopter on the surface of Mars. And what amazing technology they've been building up with these 23 instruments and audio and what have you. Okay? Of course, just a few days ago, they were working out the problem with the communication and the programming for Ingenuity, the little helicopter, getting the blade to turn properly, synchronizing the sequence of commands and what have you. But even this, just watching it turning its blade, that itself is fun to watch. We couldn't see that before in previous mission, but now we're able to actually feel like we're there. Okay? And then, of course, this morning, they had a very successful flight at 3 o'clock in the morning. This was the first shot. It's not a video, but an actual image of Ingenuity leaving the ground for the first time on another planet. Okay? I just love Mimi's response. Okay? It's just priceless. And they worked on it for 7 years, and they got the launch. All it did was go up and down. Okay? All right, well, that's all the excitement. But this is on another planet. Okay? And I think it's great. Watch Mimi's response to that. That is just so incredible. Okay? So we got the first image. You can clearly see with Ingenuity right there on the surface. And all it did was go up for 10 seconds, turn, and come back down using the twin blade. The challenge is that the gravity is 68% less than that of Earth, 100 times thinner than the atmosphere, is 100 times thinner than the Earth, and it's super cold, and all of that. And the atmosphere is made of carbon dioxide. What did they do? They did it. Okay? This is the actual high definition video that just came out this afternoon. This is high definition video. Okay? So you can see Ingenuity at the center bottom, and there it goes in flight. Okay? Twin blades is stable. Okay? Then it turns a little bit, 90 degrees, and then came back down. Okay? Now a lot of people have been asking, is that all it's going to do? Okay? No. This is just the first step. They're going to be working with Ingenuity for the next 30 days. Right? So eventually it will get flight. But how exciting is this? This is the first ever flight. And on board the Ingenuity, it's a very small sample of the Wright brothers fabric. And so this was the Wright brothers moment on Mars. What an accomplishment. Okay, so also and talk about the solar cycle. The sun is definitely starting to wake up, right? So we're seeing lots more sunspot activities. We're seeing the curvature going up to the cycle 25. And we also see some very active sunspots today. One is coming around the rim there. So we see active sunspots. There's been quite a few flares that are associating from the sun. This is an ovation today. So you can see that the flares are very active. And in Alaska, Finland, Sweden, what have you, we're coming out with lots and lots of images. We're getting close. We're not quite here in Oregon. I've seen some pictures from Washington, state of Washington, but not quite down in Oregon. So we're getting there. We can see the activities are starting to pick up a little bit. Okay? And this is today's map. You can see that Oregon is right on the very edge of that potential viewing of the auroras. I'm sure we'll get one sometime soon. So looking ahead, we'll hear more about Ingenuity in the upcoming next 30 days or so, making its flight path and what have you. So if you enjoyed today, it's going to get even better. To the planets, pretty much the same. Mars is in the evening. Jupiter and Saturn starting to emerge into the morning. Mercury and Venus are starting slowly come around into the evening. Then the object of the month would be Messier object number 3, which is a nice bright cluster. It's located right over here by Arcturus. Use that as a guide. And then head over toward M3. It's fairly bright. It contains about 500,000 stars, the magnitude of 6. So that means that you can fairly see it with the binoculars, and it's a great view. Some people find it challenging to find the cluster when it's just outside of the Arcturus. And then the International Space Station will be visible from April 25th to June 1st. So we're going to get a whole bunch after April 25th. And go to spotthestation.com, get your data. Okay? And then we have another launch. This is going to be the Crew 2 on April 22nd. If you're used to getting up at 3 o'clock in the morning like we did this morning, you can watch the launch. And they're going to send up 4 more up on the space station. So it's going to get pretty crowded up there. But this is another Dragon SpaceX launch, and it's going up. Okay? And then we have the Lyra meteor shower coming up, peaking on April 21st, 22nd. Good news, bad news is that on that night of the peak, which is debris left behind by Comet Thatcher, it's going to be 68% full moon. So that's not necessarily good news, but you can still see it. And then we have the peak that's going to be the radiant point occurred over by the constellation of Lyra. Look for Vega toward the east. Just saw Vega last night. It's high above the eastern horizon. Okay? And so that will be the radiant point. Get away from city light and get some good viewing. So the viewing opportunity will be on the 20th through the 23rd, are the best nights. It starts on the 16th and goes through the 30th, but it peaks during the 22nd, 23rd. As mentioned, this is the debris left behind by Comet Thatcher. Producing the meteor shower. Right? And then on 26th we have the full moon, but this time we're going to have perigee. So this is known as the supermoon. They're close enough in proximity between the full moon, the supermoon, the 27th of April, the moon will be below the horizon. But still, technically, that will produce a full moon that's going to be 30% brighter, 14% bigger. Right? And so then, what the bonus I want to mention, Mike mentioned this earlier, on May 26th, we have the first of 2 total lunar eclipses, right? And that will occur on May 26th, but unfortunately, at that time, it's going to be during the middle of totality, only 10 degrees above the western horizon. So, not exactly the best ideal viewing circumstance, but it is technically an eclipse at that time. But then 14 days later there'll be an annular eclipse on June 10th, and that's going to go mainly over Canada, Greenland, over to Europe, kind of a very much upper latitude. Okay? What's interesting about this is my father lived in northern Michigan. He's been asking me about this, and he's actually 5 miles away following the path 5 miles when it'll be below the horizon. If he goes up 5 miles, you'll see it. Right? So we have lots of opportunities in the next couple of months to do some great photo opportunities for the month of May and April and May. And so take those pictures and you can submit them for the RCA calendar in 2022. And that is it. Stay healthy, everybody. That's a lot of information, but that's a lot of excitement that's going on in the nighttime sky.
Thanks a lot, Jim. Yeah, during the press conference, Mimi said that she kept asking when she's going to be able to have the big party for Ingenuity. And I guess now they're feeling like maybe the big party is warranted. I noticed I haven't been introducing myself. So for those of you who are new, I'm Mark Martin. I'm the VP of programming for the club. I arrange the speakers. So in particular, if anybody has any speakers they'd really love to hear from, just drop me a note. But tonight I'm going to introduce our speaker. Our speaker tonight is Dr. Yvette Sendis. Dr. Sendis is a postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics. She's a radio astronomer focused on understanding short-duration astronomical events and variable astronomical objects. She received her PhD in astronomy from the University of Leiden in the Netherlands and master's and bachelor's degrees in physics from Case Western Reserve University in Cleveland. As an undergraduate, she worked with one of our very popular previous guests, Dr. Jill Tarter at the SETI Institute. Dr. Sendis has written popular articles for science magazines such as Astronomy, Sky and Telescope, Scientific American, and Discover, and has appeared on radio and television. She was a regular contributor to the Astrobytes website and is well known for her Astronomer Here comments on Reddit. Please give a warm welcome to Dr. Yvette Sendis.
All right, hello everybody. Do you guys see my title slide? All right, then I'll take it away. Hello everybody. Thanks very much for the virtual welcome to your meeting. Very excited to speak here tonight. It is going to be midnight by the time I'm done with my talk though, so if I yawn once or twice, please forgive me. I am a radio astronomer. I don't have to stay up all night. It's not part of my job. But I'm going to tell you what is part of my job today, which is basically studying cosmic explosions of all sorts in the depths of the universe, studying them mainly in radio astronomy, but sometimes I've done some other frequencies as well. And I'm basically going after the biggest explosions that we have in the universe. So sort of things like supernovae, exploding stars at the end of their lives, or tidal disruption events, where if a star wanders too close to a supermassive black hole and gets shredded apart, then that can cause one of those. So that's the sort of thing I'm interested in, and that's what I'm going to talk to you guys about today. So just to change slide here, yeah. To give a quick overview for those who don't maybe remember their high school science class or whatever, I wasn't quite sure what everybody's background was here. So this is the electromagnetic spectrum. We have different kinds of light that we study. Most people, are in the visible part of the spectrum. So your eyes, your amateur telescope, all those things are going to be in that one little part of the spectrum. But there's a lot of different wavelengths that light emits at. So basically when photons go out from our various astronomical sources, and they will span at the smallest they're the gamma ray wavelengths. Then you go X-ray, ultraviolet, visible, infrared, microwave, radio. And some of these you do from space and some of them you do from the ground. So, you have your giant Mauna Kea telescopes you do on the ground, things like that. And radio astronomy tends to be on the ground compared to, say, a space telescope. So why do we do that? It's because the Earth's atmosphere blocks some wavelengths. So of course, if you look out and it's a little bit of a twinkling star, that's because the seeing is not very good. Some of that light is being blocked at wavelengths. So the visible light, most of that will come through without too much trouble, but you'll probably go to a mountaintop if possible to observe, if you're an optical astronomer, to minimize the obscuration of that light in our atmosphere. Lucky for us, those gamma rays and X-rays, and those are blocked by the atmosphere, so we don't have to worry about them on the surface of the Earth because Earthlings don't really like that. Then you start getting some obscuration, mainly from water vapor, when you start going to the longer and longer frequencies. So you have infrared is blocked, so you go into space, or you can fly a telescope called SOFIA in the upper stratosphere, which I've actually been on. That's another talk for another day. And then eventually you start getting this beautiful hole, and this is where most of radio astronomy lives. And this is why radio astronomy is, one of the reasons it's a very powerful thing, is it's basically like going into space, but you don't have to do it in terms of astronomy and the sort of stuff we can do. We still will have some effects. So, if there's a radio frequency interference, so if somebody has a cell phone too close to the radio telescope array, that will cause you problems and things like that. But then you keep going down, eventually it's in kilohertz. So like your AM band on the radio, those wavelengths will start to become blocked again. But I'm usually up here in the gigahertz regime is roughly where I'm doing my science. And I can just see everything as if I was in space. So that's always pretty nice. And so, there are, of course, differences. Why do we look at different parts of the spectrum? The reason is there's different kinds of physics will give off different kinds of light. And I'm interested in different kinds of physics than my friends who do optical astronomy. So, if we're optical astronomers, and I think most people are familiar, this is the Milky Way, this is the Southern Hemisphere, because we have two Magellanic Clouds in this. And this is what you see if you go out into the, dark, really not light polluted skies. But if you had radio eyes and you looked up with your radio eyes, this is actually what you would see. So what we see here is, so you do see like the wispy things and things like that, these circles, those are supernova remnants. Those are in our own galaxy. And I'm going to explain a bit more about those later. The interesting thing here is all of these dots, so the little dots that look like stars in this image are not actually stars. Those are actually by and far, with maybe one or two exceptions, active galactic nuclei, so supermassive black holes at very large distances from us that are just spewing out radio radiation as, little bits of gas or something comes too close to them and they emit. So that's really a lot of the radio sky. What we're seeing are just these very, very far away galaxies and these very close supernova remnants. Some other things, but then you're probably going to need more processing. But most of the brightest sources we have are these in radio are remnants in our own galaxy. And then these things further away. I should also point out, I'm also a radio astronomer. I make radio pictures. So I'm talking about, making radio pictures, and this is what it looks like. If you're, say, an astronomer who works in pulsars, so very short pulses and stuff, your radio sky probably looks a little different, but So what do? As I said, I search for radio transients. So this is what I showed you guys earlier, is a picture of what the sky looks like when it's not changing. But of course, there's always things that are changing in the sky. If you're an optical astronomer, you have solar flares that you guys were just talking about. That's of course a transient thing on our sun. If you are a very good alien astronomer and pointed a telescope, you would see the photometry of the sun change as like the light changed in its brightness from the sun. But I'm interested in radio transients, and these are basically just the radio things that change in the sky over time. And there's a lot of different things that will do that. It's usually something if the system is changing over time. So a space explosion, an explosion that takes place in space, of course, you are going to have a lot of changes happen very quickly, and then that's going to really affect things, and you're going to see results from that in radio. This is one of the radio telescopes I use, the Very Large Array in New Mexico. Yeah, I should say, I always wanted to be an astronomer since I was 13, and I read a book on it. Then I said I wanted to be a radio astronomer when I saw Contact with Ellie Arroway in it, like running around this radio telescope and all that. So, Contact is responsible for everything. And then, yes, it was very cool then, of course, to work for Jill Tarter. That was about 10 years ago now. That was a pretty cool accomplishment in my career. But we did not find aliens, is always what I say, because then this wouldn't have been the first time you heard about this. Anyway, so there's a lot of things that go explode in the night. I'm first going to tell you guys about supernovae. So just to give a quick overview to people to remind you what exactly a supernova is, why do stars explode? So if you're a small star like the size of our sun, you are not going to go supernova at the end of your life. When you start running out of the fuel, when you're converting hydrogen into helium, you're just going to start poofing out into a red giant, which is probably going to swallow our Earth someday in billions of years from now. But when you run out of that fuel in the core, you're just going to become a pretty planetary nebula, and poof out those outer layers and leave behind a white dwarf in the middle. If you are a larger star, though, about 8 times the solar mass of the sun, you are going to go supernova, which is less than 1% of all stars. And this is basically the hydrogen and helium is fusing. You start swelling out into red supergiant. When you run out, the core collapses on itself. That bounces back and creates a supernova, which leaves behind either a neutron star or a black hole. A neutron star is if it's 8 to 18, solar mass is 18 times the mass of the sun. Black hole is, we think, bigger than that. So yeah, what happens when the supernova explosion happens, though, and what I'm very interested in is the shockwave starts traveling outward, and any material that was already existing, let's say the star expelled before it died, that shockwave is going to hit as it's traveling outward, and that is going to make electrons spiral in magnetic fields, and that creates radio radiation. It's called synchrotron emission, for those who are more technical. And the idea is then, as this is going outward, you can sort of study how the system is going to evolve. So one of the most famous objects I've studied is one called supernova 1987A, which is very creatively named that because it was the first supernova found in 1987. And the thing that's interesting about supernova is, as I said, less than 1% of stars go supernova. And that translates roughly in our galaxy to about 1 star per century, we think, goes supernova in our own Milky Way. The problem then, of course, if they're very rare and you're only seeing about, the last time we've actually observed a supernova was 1604. It was called Kepler's supernova. Galileo actually observed it, but he didn't have his telescope yet. So supernova 1987A is special because it's the first one we could observe since the invention of the telescope that was the closest one to Earth, and you could actually see it with your own eyes and all that exciting stuff. So if we have our Milky Way, we're going to go look a little closer. This is the Large Magellanic Cloud, so one of the satellite galaxies of our Milky Way, at 170,000 light years distant from Earth. It's a southern hemisphere object, so unfortunately you can't see it from Portland. But if you go there, you actually have this beautiful nebula called the Tarantula Nebula. You basically have, as the Large Magellanic Cloud is orbiting, you have tidal friction, even at that great distance from between the Milky Way and the Magellanic Clouds. And it's stirring up, it's the largest star forming area we have in the local galaxy. The thing that's really nice about it is, so our Milky Way, you have, of course, a lot of dust. We can't see a lot of the Milky Way versus this. You can actually just point your telescope and see everything that's going on. Most of the most supermassive stars that we know of in our local galaxy are actually discovered in the Tarantula Nebula, just because you have that straight line of sight up there. And way on the edge of the Tarantula Nebula, in 1987, as I said, you had supernova 1987A. So it was actually discovered, there's a University of Toronto astronomer, Ian Shelton, and I did this work when I was at University of Toronto, so I'm obliged to say that contractually. But him, and then there was another Chilean astronomer, but Ian, he was just a telescope op. He wasn't like a professional astronomer at the time. He just had his bachelor's degree type thing. And he was imaging the Magellanic Cloud. At the time, you still use these giant glass plates to do astronomical imaging. You didn't have digital imaging yet. And the idea was that he was having trouble with his equipment that night, so he decided to end things early, but he was going to develop his glass plates before he went to bed. And he went and he looked, and there was a really bright star that hadn't been in the Large Magellanic Cloud the night before. And he was like, wow, that's so bright, I should probably be able to see it if I go outside. And he went and looked out and saw it, and his Chilean colleague was like, do you see this? And they both saw it, and they realized it must have been a supernova. The telephone system at the time was actually down. This was the Las Campañas Observatory in Chile. They had to drive almost 100 kilometers or something, was what Ian told me, to put the telegram in to say that they discovered the supernova. And it was actually very lucky that they did, because there's several other people observing that night who also discovered the supernova, but Ian was the first one, so he got the credit for finding it. There was an amateur astronomer in New Zealand who also made a discovery that night, for example, and things like that. So, you know, always develop your plates before you go to bed, I guess is the thing. Anyway, so supernova 1987A was very exciting. You could actually see it in the Southern Hemisphere for about a month with your naked eye. It was the first time in hundreds of years you could do this. But it was also a very strange supernova. So the first thing is, it was, as I said, that bright that you could see at that distance. but it's actually about 10 times fainter than what you expect from a normal supernova explosion. They have a usual certain luminosity in the sky. And that's quite interesting because, of course, we wouldn't have actually been able to see it outside of our local galaxy. It was that much fainter. And that's kind of because, yeah, okay, how often are these, do these happen? We don't actually know. There's a lot of questions. How did this occur in the first place? The second thing that's really notable about supernova 1987A is you also had the first occurrence of neutrino particles discovered from outside of our solar system. So what are neutrinos? They're fundamental particles like electrons or something like that, but they don't really interact very much with anything, is kind of the main thing about neutrinos. So if you're at home right now and you're watching this talk and you do a thumbs up right now, like I'm doing, then every single second, about 100 billion neutrinos are passing through the tip of your thumb. That's how, like, obviously it's been happening all your life. They have not affected you till now. They're still not going to affect you for the rest of time. But neutrinos are everywhere, and they're just very, very hard to detect because they don't really interact much. So to give you an idea of how you do this, this is actually a neutrino detector in Japan. The idea here is these are all little detectors. You fill this up with water. For a sense of scale, that is 2 men in a boat, to get an idea of what is going on in this system. And when you fill this up with water, you're looking for very faint light flashes as the neutrinos sometimes interact with a stray particle, and then you know neutrino happened. But anyway, one of the biggest creators of neutrinos in our entire universe are actually supernovae. So it's basically as that collapse is happening and as the neutron star is being created, a huge burst of neutrinos, as many as there are atoms in the sun, are created in just a few seconds. The fascinating thing about this also, by the way, is the neutrinos, and we know this because supernova 1987A, 3 neutrino detectors on Earth detected about 18 neutrinos. This was, as I said, very unprecedented and all that. But they detected it a few hours before the visible light was detected in Las Campañas in Chile. Okay, what happened? You can't travel faster than the speed of light, of course. So these neutrinos don't really interact with everything. When they got created, they could immediately escape the center of the star. All of the light and everything that got created, on the other hand, I mean, there's still how much star you have to work through for the shockwave and for all that electromagnetic energy to escape. So that took a few hours for that entire process to reach the surface and then start traveling toward Earth at the speed of light. But as I said, the neutrinos, they travel at the speed of light, and they did it a few hours earlier. And the cool thing is there's actually a supernova neutrino alert system. So you can go Google this while I'm chatting if you're interested. And you can sign up to get alerts if all the neutrino detectors on Earth suddenly go haywire, probably because there's a galactic supernova, and you'll have a few hours so you can go out and try to find it yourself, which I'm signed up. They've never had a false alert, so that's either really good or really bad. I guess we'll find out someday. But so that's kind of one of the cool things about a supernova neutrino alert system that we know from 1987A. So anyway, after the flash and bang had passed from supernova 1987A, and once they launched Hubble and once they fixed Hubble, they finally pointed Hubble there and they saw this, which I'm sure you've seen this image before. It's of course very famous. It's kind of this weird circular structure. I'm going to show you guys, this is an artist's conception that Sky and Telescope showed of what we think the system really looks like. So on the left here, this is kind of that Hubble view. But it's basically, we're looking at a strange angle, and this is really what we think the structure around supernova 1987A looks like. And I didn't fully appreciate until I started studying this object. This is actually what we saw is pretty much all from before the supernova explosion actually happened. So we think this is all this innermost ring. The innermost bit, of course, is the actual supernova remnant itself from the star that it exploded. But if you're looking at, say, the purple ring around here, this inner ring, we think that's a swept up ring of red supergiant gas. And then you have these outer rings, which are from earlier mass loss. Oh, and I'm sorry, I forgot a very important detail. I said a red supergiant is what goes supernova. Supernova 1987A was actually a blue supergiant that went supernova. It's the only time until then. Nobody had even predicted theoretically that that was possible. But it was also a blue supergiant, so that was really strange. And what we think happened is it was a red supergiant, so toward the end of its life. It underwent some sort of merger, perhaps with a stellar companion. We know most of these supermassive stars are actually binaries. And then tens of thousands of years after, roughly, based off of, you know, how long this structure had to go outward, the star exploded in a very strange supernova explosion that is not really like any other supernova explosion we've seen. So there's clearly a lot of things that are going on in supernova 1987A that are very unusual. And, you know, this understanding this structure is really important to that. So what is my job here in all of this? Because this happened a very long time ago, and I started my PhD not that long ago. So the way I always explain it is we're observing over time, and we're seeing what is happening to this object and how it's evolving as a supernova remnant, and then hopefully figuring out how it all began. So here in the left is a picture of supernova 1987A from February 24, 1987. This is me on the right in 1987. So why I always like to explain what we're doing is, you know, you look at that, I was, you know, obviously toward the beginning of my life as well. And then you could look at me if you were an alien anthropologist or something and say, okay, she started little and cute, and then, you know, she got bigger, and then what happened? Well, let's try to figure this out. We're basically doing the same thing right now in astronomy with supernova 1987A. It's like, okay, it started here and it's been expanding outward, and, you know, what is going on? Let's figure this out by watching how this story unfolds. So to observe supernova 1987A, this, as I said, was part of my PhD process. People have been observing it since 1990, was the first radio mission with this Australia Telescope Compact Array, Southern Hemisphere object, the very large array in New Mexico can't see it, unfortunately. But this is what that telescope looks like. For scale, the line here, these are railroad tracks. So basically you can move the antennas to different configurations based off the observation you want to do. And so yeah, they've been observing it since now 1992. And I basically took data, it was like from 2013 to 2017. So sort of a more recent part to see what exactly was happening here. And then of course, if you have this really nice data set that goes on for, you know, decades, what are you gonna do? You're going to make a movie so you can show it in your talks. And so, as I said, this started in 1992, and what you're seeing here is, as I said, this shockwave is expanding further out, and it's going to slam into everything that it encounters along the way. If it slams into more material, you're going to get more radio emission. And yeah, so what you can do as a radio astronomer is you can say, okay, first, for example, it gets brighter on the left, and then on the right, is that physically something happening in the system? Is that maybe just the explosion was asymmetric, things like that? Around 2003, as you see, it starts to get super bright, much brighter, much faster than it was in the earlier images. And what we think happened there was that the shockwave encountered that first closest ring that I showed you on that image, and it basically shredded it apart. And then in 2017 or so, or sorry, 2016 or so, I saw in my own research that it basically finally went out, because you can see this ring structure change very carefully. And we also see that in other wavelengths as well with Chandra and Hubble Space Telescope and things like that. If you kind of want to see what these images look like individually, so I have another hobby. My hobby is cross stitching, which is, you know, sewing very carefully. And I actually made this for my PhD supervisor when I finished my PhD. It is the first figure from my first paper that we did together. And this is the evolution over time of supernova 1987A from 1992 to 2017 in radio at 9 gigahertz. It is all astronomically accurate. So if you want to look at the zoom in, this is the right ascension, this is the declination, this is the beam model. So basically the resolution we have with the radio telescope. And this is all actually, because, you know, most astronomy these days is just pixel art, right? So it actually translates beautifully, and you just have to be very patient, and this takes a little longer than actually processing your images any other way. So yeah, this was a very cool project. I should also note that this was also very nice because my supervisor actually made the first few images in this series for his research as part of his PhD project. So it all comes together. The only problem is I didn't leave room here for the next students so we can stitch them on, but I guess we'll figure that one out later. Anyway, so we're studying supernova 1987A. It's a very cool object because this is literally the best picture you are going to have of what a radio supernova looks like until we have one in our own galaxy. And, you know, we're studying how it's evolving into a remnant, all sorts of interesting things like that. We do still have some questions, you know, beyond how exactly this explosion happened. We don't know 100% why exactly it happened. First of all, what's at the center of supernova 1987A? We started in the past year or so, there have been some radio observations that have been very intriguing, which were basically indicating a pulsar wind nebula was in the center. So this is, a pulsar is, a very famous radio object. If it starts interacting with, if a neutron star starts interacting with the material around it, it's going to create a nebula. Even if that pulsar beam is not directly pointed at you, you can see eventually evidence of the nebula. This is kind of one of those, you first get a little bit of evidence, but a lot of people think it's not quite strong enough, and you get a little more, like, and then eventually, the snowball rolls down the hill and you have a giant snowball that will take out your house. This is kind of like, we're still just, it's like starting to roll a little, I guess is the best way I can explain. It looks like there's maybe a pulsar wind nebula, but a lot of people aren't convinced yet. I can hear you ask, what about a black hole? Why do we not think there might not be a black hole there, or what's going on? Well, we do know that we can see the star that exploded. As I said, we could see, it was a blue supergiant star, but we don't think that star was massive enough to create a black hole. Like, we're not 100% certain because it wasn't a very interesting star for about to explode terms, but right now we don't think it was massive enough. But that does give me a good segue into the next part of my talk, which is a bit more about black holes and the explodey things they do. So this picture is pretty famous. It is, of course, a picture of a black hole. It's called M87 star. In M87, 53 million light years away, and billions of times more mass than the sun, captured by the Event Horizon Telescope, which is radio telescopes linked all over planet Earth. Basically, if you make your radio telescopes link together at greater distances, you can get to smaller and smaller precision, which is also just really, really hard to be very clear. Like, that's why you don't do it all the time, but you can sometimes get amazing things like this. You can see different parts of the black hole as well from this. So what we can see is this is the event horizon's shadow, so you can't get the light out of there. This is the rotation axis. And this is, for a sense of scale, the orbit of Pluto, to give you an idea of how big these supermassive black holes are. They're truly supermassive. And something that doesn't fit in the Event Horizon Telescope picture, but is also very interesting about M87 star, is it also is launching, it has launched this relativistic jet that is going outwards from the galaxy, and it is 5,000 light years long. So it's been going for, thousands, probably millions of years, and it's spewing out this radiation. The reason I also think these relativistic jets are very interesting, though, is we don't actually understand how they're created. So, of course, there's particles, they're interacting somehow with this black hole and they're getting launched, but we don't understand what makes them relativistic, is really like kind of the way to explain that. And that's, one of those big open questions about astrophysics, and a lot of people are studying that today. But one of the great ways you can study that and maybe try to figure out what exactly is going on for these supermassive black holes and why they're creating these jets is by studying tidal disruption events. So tidal disruption event is basically when a black hole gets a star gets too close to a black hole, wanders into its radius, and it gets basically tidally torn apart. So that's why it is a tidal disruption event. So let's see if my little animation will start. So yes, here we have our black hole with its event horizon. And what we're going to see here, this is a supermassive black hole at the center of a galaxy for scale. The little ones created by stellar size explosions are probably not big enough to have that many of these come too close to get torn apart. And you have this star, and it's going to start wandering a little too close. And it's going to get a little elongated first, is actually like one of the details of what the theorists tell me, at least. And it is going to start getting ripped apart. About half the material we think will fall into the black hole itself, but about half of it will create this crazy accretion disk. Sometimes it will launch jets. So this animation shows one that's launching a jet. Sometimes it's just in this accretion disk. And basically this outflow is going to interact, much like that supernova shockwave did, with all the material surrounding it. And this can go on, this radio mission can go on for many, many years. We can study it as it's interacting with its surrounding environment. And they can, in fact, even launch relativistic jets, a very small subset. I'll tell you guys a bit more about that in a bit. Will actually launch relativistic jets that we can study, and we can see one turn on, which is pretty cool. So yeah, my research on the TDEs. Use telescopes like the VLA. I also use Meerkat in South Africa for those South African or for those Southern Hemisphere objects. And I have a collaborator on ATGA, so we link together to get our observations as we want them. And yeah, so this expansion outwards will last for years. And what we basically do though for this, because these are way too far away to see the detail like what I showed you guys on supernova 1987A, is we're going to take observations at multiple frequencies and not just at 6 gigahertz. We're probably going to do something like 1 gigahertz to 20 gigahertz. It kind of depends as the object evolves. And you're basically going to take the flux measurement at every single point for this object. And then when you have the flux, so how bright it is in the radio, you will get what's basically a light curve. You know, you can just plot your frequency and your brightness. And you can actually then take physics that was developed by a lot of very clever people. I did not figure it out exactly. I just know how to do it. And you can get all sorts of things like the radius of your outflow as it's expanding over time, the energy that is in that outflow that is giving off this radiation, the magnetic field that is in that outflow, the density of the material it's plowing into, all sorts of things just from basically getting a few data points, you know, and their brightness, which is pretty impressive, really. Just to give you guys an example of what sort of tidal disruption events happen, this is actually, you know, we're going to go back to the start. The start for this, though, is only 10 years ago. It's actually, you know, 10 years ago within a month. This is really a very new field. So people have found some evidence of tidal disruption events before this, but this was the first one that everybody was indisputably, yes, this is a tidal disruption event. And this was also the first radio detected one. It's called Swift J1644 plus 57. Because the Swift satellite was what discovered it, and it was a source 3.5 billion light years away. So the Swift satellite, it looks for gamma ray bursts, which are another type of gigantic space explosion I don't really have time for, unfortunately, in this talk. And basically, there's two kinds. There's a short gamma ray burst, there's a long gamma ray burst. The long will still, like, even though it's called long, will only last a few minutes. And basically, this was a gamma ray burst that just didn't turn off. Like, it was kind of low level compared to GRB, but it just kept going. And everybody realized, wow, this is crazy. Something new is going on. And what it turns out it was that a relativistic jet, as I said, was launched from this black hole when this star got too close and got ripped apart. The even crazier part is after 1.5 years, it actually turned off. Now, this is amazing because, I mean, that relativistic jet I showed you guys where it's 5,000 light years long, obviously that takes much longer than a human lifetime to get together. This is something, I mean, you can cover that in a postdoc, you know, like that is a really short-lived object. If you're into these sorts of things, that is a very nice data set, you know, it's a very exciting thing. And the other interesting thing I should mention is, so there were two other of these relativistic jetted tidal disruption events discovered in 2011. They were at greater distances, so not as useful. And we haven't seen any since. It's not for lack of looking. They just appear to be very rare events. I checked, you can't really order them on Amazon, unfortunately. So we're just kind of at the mercy of the universe and what it's going to send to us. But the interesting thing is, even though that relativistic shockwave is gone, you still have that outflow going outward, just the normal one, and you actually still see radio emission from it. There's another cross stitch. Guys, I really like to collaborate with people because then, you know, I make us a cross stitch. It's, you know, it's really nice. We all need our hobbies in this pandemic. But yes, they're much less exciting for these objects that are billions of light years away. It looks like a dot. The right here is the VLA image. As I said, you're just going to have a bunch of these that are a bunch of frequencies, and you just measure how bright that dot is. And then, yes, this is on the left, Swift J1644 plus 57. So that is an example of, you know, the most extreme tidal disruption events that we have. Then we have sort of the more, quote, normal ones. I hate to say normal because it's still like such a fascinating event, and they're much more rare than supernovae, I should emphasize as well. So we have maybe about 100 known TDEs right now in the literature, depending who you ask. So they're really not that common. But this is a more, quote, common tidal disruption event. So what we think is more typical for what we see in these events. So it's very luminous in the optical. So that's why people noticed it. It was actually, you know, you have these giant surveys that will survey the entire sky at night looking for supernovae. And they will sometimes see something that's much more luminous. And if it's at the center of the galaxy, it's probably a tidal disruption event. We get interested in that. And this was a black hole that was 30 million times the mass of the sun, 750 million light years away. So compared to the last one, 3.5 billion light years away, this is right next door. And the thing that was really exciting for me, so this was an object I was working on, was we actually, in addition to the VLA, had the first published occasion that the Atacama Large Millimeter Submillimeter Array called ALMA detected this object. This is kind of the newest telescope that the National Radio Astronomy Observatory is working with right now. So it was a few years ago. And the reason it's down in Chile at a very high altitude. And it's because I showed you that image at the very beginning, water vapor. When you start going up, almost at about 100 gigahertz, I was down, at 6 gigahertz at the beginning of this talk. When you start getting there, you start getting that water vapor and issues from it. So if you go up into the high regions of Chile, you don't have those effects and you can do a lot more astronomy. ALMA is a very powerful instrument because it's really in this regime that hadn't really been probed to much sensitivity before. And the thing that's really cool is this emission that I've been talking to you guys about, these outflows from supernova, it actually first starts in the millimeter. So it starts in the band that ALMA is at. So it's actually very exciting. Then the signal, basically as it goes to lower frequencies over time. But if you really kind of want to see what's going on at the very beginning, you get this ALMA emission. So we got the ALMA emission, we got the VLA emission. We could do very, very precise modeling of what was happening in the system. And I should also note that if you ever want ALMA time, anybody can apply for it. It's open skies. Anybody in the world, you just have to have an idea. Except the deadline is once a year and it's day after tomorrow. And so I have 36 hours or something. But my proposal is pretty good before I came to talk to you guys. But it's going to be a super luminous supernova telescope proposal. So maybe, once this pandemic is over, I can come and tell you guys all about that and how that goes. But anyway, so just been on my mind lately. So, AT 2019 DSG, as I said, it's a lower energy supernova, more typical of what is going on in these. So what do I mean by that? So if you're looking and say, as I said, you have all these parameters and you're looking at the energy and velocity of tidal disruption events and you're going to plot it. If I have my mouse, I'll point out here. So this is basically just velocity. And this is where something is between relativistic and non-relativistic is what we're showing on this x-axis here. And what we're showing here is the energy, how much energy has been pushed into that system, into that outflow that we're seeing in the radio. So if we have the relativistic one, Swift J1644 plus 57, it's actually over time becoming less relativistic. It is now no longer relativistic. So we're seeing it slowly lose energy. It's still very energetic because it had that relativistic jet fueling it. As I said, it was on par with what a gamma ray burst is, like what you detect. And then if you were to say, okay, let's talk about this AT 2019 DSG object, it's way down here with all these other tidal disruption events that have been discovered over the year. And these little blue stars here are what you basically expect in terms of energy and velocity from supernovae, like the supernova 1987A. So it's very interesting that we're starting to see this spread of what sort of transients we have. And there's clearly two different categories. One is much more rare than the other. We don't know why one is in one category and one is the other. As I said, this is a field that's really just starting. So this is really the exciting time where you're trying to fill out what exactly is happening, what is going on here. And I've kept busy this pandemic, just, working on filling in this plot here. So that's always been good. The other one I really like, though, is you can also study the density surrounding these tidal disruption events. And this is very powerful because basically every single time we take a radio observation and this this shockwave has gone outward, this outflow has gone outwards, we get another reading. And what happens is, of course, we're doing this several times over a year once we see something is radio bright. And then we kind of start filling in as you're going out from the black hole, what we see in terms of density. So this is a bit of a complicated, the problem is, so if you have a black hole like M87, so the one that, we have the black hole picture of and things like that, it is several, thousands or millions of times more, not millions, but more massive than Sagittarius A star, which is the black hole at the center of our Milky Way. So it's kind of apples and oranges if you were like just saying like, okay, I'm going to take however many parsecs or light years or astronomical units from the center. What we do is then we divide by what's called the Schwarzschild radius of the black hole. So like basically how massive it is, how big its event horizon is. Then you kind of have a scale that's, yeah, okay, this is maybe getting too technical. Sorry about that. The point is this is radius and this here is density. Density is in centimeters per 1 atoms per centimeter cubed. So for example, you have 1 atom roughly. If you had a random bit of interstellar medium in every centimeter, 1 to 10 atoms would be an average interstellar medium. So what we can do is we can look here and we can see that, you know, most of these, as you're going out from the center, most parts of that galaxy, it starts to become less and less dense. You can start seeing things like, oh, it's interesting that Swift J1644 plus 57 and M87 are roughly the same densities. Is there something there? You know, we don't know. As I said, you can't order those on Amazon, unfortunately. The one I really like, and I want to point out here, if I get my mouse back, there we are, is so this is Sagittarius A star, and this is the best density profile we have around our own Milky Way. And we can't get a better one because there's a lot of dust. So it's a very complicated thing between us and the Milky Way. We now know all of these galaxies' centers to much more precision that we know for our own galaxy from studying tidal disruption events. Even though they're, you know, millions or even billions of light years away from us, we actually now have this incredible, you know, idea of what sort of densities we have surrounding, you know, those innermost regions of supermassive black holes from studying this. So I think it's a very good example of, okay, you have an event, but you can learn often several things from that initial event in astronomy. You know, once you have one technique and you keep applying it, you can learn all sorts of things come out of it that you weren't really expecting. So yeah, just to wrap up here, I hope I convinced you guys that radio astronomy is a powerful tool for, you know, a lot of things, but for understanding transients, sometimes transients that are, you know, take years to go to unfold. For supernova 1987A, we can see the reacceleration of the shockwave as it's left that innermost ring, and we can see it going outward and propagating outward. For tidal disruption events, we can learn a lot of different things like its energy, its radius, its density, things like that. And there appear to be 2 tidal disruption event populations, but we still don't really understand why. So we still have a lot of work to do there. So thank you very much.
Thanks a lot, Yvette. That was really nice. So, so there were some questions that appeared in the chat.
Sure thing.
The way we've been doing questions typically is I'll read them and then as they come on so that you don't have to pay attention to the chat. But if
Sure.
you would rather read them yourself, that's fine too, whichever one you like.
I wouldn't mind if you read them, just because in case I want to go back to slides, it's usually better to not stop sharing the screen and find the chat. Yeah.
Great. So the first one was, what was the maximum magnitude of supernova 1987A?
I don't know the exact magnitude. I do know my supervisor was a 13-year-old in suburban Sydney and could see it. So that would be maybe like 4th magnitude or something, I guess, right? If you can see it in the suburbs. I mean, roughly, I'd say.
Great. And Jeff was wondering what the velocity threshold is to be called a relativistic jet.
That's a good question. So the problem is in a lot of physics, so, you know, there's non-relativistic, that's if you're, you know, you're at the speeds we're all used to. And then there's relativistic, and you start to say something is mildly relativistic when it's 10 to 20% the speed of light. It's usually what you do. The problem is it's not like the physics is worked out for these systems where you're mildly relativistic. There's still a lot of uncertainty of how one ends and the other begins. So yeah, usually we'll say 10 to 20%, but there's this, it's not like it immediately has all the characteristics of relativistic.
Great. So if you have questions, please enter them in the chat. Craig is wondering what the angular size of supernova 1987A is these days.
Well, let's find out. I think it's the whole thing is about a little over an arcsec. but I actually have the scale on this cool little plot here, so. Yeah, it's about 2 arcsecs, I guess, if you're looking here. Yeah. Okay, so it's an arcsec in radius, I guess is the answer there.
Thank you. Gary is asking, do the arrays of Earth-based radio telescopes provide a full view of the night sky, or does the Earth eclipse what you can see?
That's actually a really good question. So the answer is, I mean, it depends on the radio telescope, is of course always the first answer. The second is the field of view is not that big for, say, a telescope like the VLA. It maximizes its sensitivity, and then the size of the sky is going to be relatively small because you're also adding together dishes, so you're really able to look at a small part of the sky. When I say small, I mean a 1/2 degree field of view is pretty big in radio astronomy for sure. So like the size of the moon in the sky or something would be quite large, which is very nice, by the way. Quarter moon outside my window there. Yeah, so something like the moon would be pretty big. I always say this is a slight problem for things like SETI, because if the aliens were ever messaging you from the other part of the sky and you were pointed there, you'd have no way to know. That's not how radio astronomy works, of course. Some telescopes will have a larger field of view. Like there's a new radio telescope in Canada called CHIME that looks for fast radio bursts. And they're basically a drift telescope. They don't point, they just let the entire sky go overhead, have a huge field of view to pick up these rare fast radio burst signals from all over the sky.
So he was also wondering if you rely upon space telescopes to supplement your observations.
So I do. So in my Swift J1644 plus 57 paper, there was some Chandra observations that we had, which were basically the X-ray was still there, but decreasing. But it turns out by the time I got to my paper, there was no more X-ray. So that was, the end of my stellar X-ray career. Sometimes you'll go and, just double check, like, if something's high energy, is the flux there, something like that. But Chandra is really the only time that I actually went and used the X-ray images proper. So
great. Mark is hoping that you can explain radio telescope beam shapes a little bit.
Okay. This is a little more complicated. I'm trying to see. I think I have a picture of, yeah, the VLA is kind of just easier to explain usually. So let's see. Yeah. So the VLA or any radio telescopes like ATGA is just in one line. And basically the beam shape is dependent on the configuration of your antennas. Then you're adding them together. So if you have, say, a single dish antenna, like what Arecibo was, or Parkes Observatory in Australia, so these big single dish ones that I'm sure you've seen pictures of, that's pretty easy because it's just one antenna. Okay, it's going to be a circle. This is basically, the VLA is in an upside down Y shape is kind of what it looks like, and it's 3 eggs. And the idea is that you're trying to get it equal so that it's a circular beam. Because something like ATGA is it's slightly ovaloid, and it's like a little annoying because basically it's just the coverage of the sky that your antennas have is kind of what goes into the beam shape. So that's really kind of how it works. The resolution depends on how many wavelength or what your longest baseline is. Well, basically, if you have a longer baseline, like the Event Horizon Telescope, which is literally all of Earth, you will have a very small beam size and you'll have very precise resolution. Most people do not do that.
Thanks. So Howard is wondering how the rotation axis of the M87 black hole is determined and whether it's based on the relativistic jet.
It actually is. We think those relativistic jets get launched out of the poles for these things. So then if you see the orientation of that jet from Earth, then we can figure out the orientation of the black hole itself. I don't think that's in the Event Horizon image itself, which I suspect is the follow-up question, but I'll have to think about that.
So Margaret is wondering if you're a member of the Embroiderers Guild of America.
I am not, but that sounds like fun. So I will say, by the way, that supernova, and I have a British cross-stitch magazine that published that. So, you know, it's like astronomy outreach in the oddest of places. I haven't stitched the AT 2019 DSG one yet, though. I guess maybe before the paper gets published, I'll have to do that. So.
Maybe you can stitch a telescope.
That is true. I'm trying to think. I don't know if I've done that yet. I usually do the things that I look at, I guess.
So Brian is wondering how you measure the density and magnetic field of the material around a tidal disruption event.
Yeah, so that's a good question. So as I said, you have your flux, so your brightness, and then you have also things like at what part of the frequency spectrum was it at the brightest and things like that. And then you basically take these inputs. First, you're calculating your radius. So there's a lot of, you put these parameters in. As I said, I was not the one who came up with this equation, but I cite the guy who did in my work. And then you get the radius. And once you get the radius, then, you can get your magnetic field out of that, because electromagnetic spectrum, we understand how that works fairly well. The density is kind of interesting because you do have to specify the volume yourself. So you have to say, I think this is spherical and there's maybe a shell radiating of this thickness or things like that. You do have to put some assumptions into that. And, or if it's a jet, okay, I think it's a jet with an angle of this or things like that. So you're going to have to make some assumptions in order to figure this out. As long as you're clear with your assumptions, people are usually okay with that. And especially if you just say, publish the numbers you use to put in themselves, because then they'll just go and take those numbers and do whatever model they want, is usually how I think a lot of this science goes. So.
Steve is wondering if you can tell us what approximate timing accuracy was needed to synchronize scopes for the event horizon images.
That has to be within like milliseconds. It's a very, very, as I said, difficult thing to do. I know this because actually just within the past week, they basically do a run every year. It got canceled last year because of COVID, of course, like many things. It's canceled the year before because actually there's a Mexican telescope in it and they had bandits try to take some astronomers hostage. So it was pretty crazy. But this year they did have enough telescopes. So they did try to go and do that. And yeah, you basically have to do everything that precisely. The problem is, so one of the essential baselines is there's the South Pole telescope, literally at the South Pole in Antarctica. And you can't maintain that level of precision that you need to get these to happen. So they actually still take that data on disk and will ship it, because right now you can't go to the South Pole. It's shut down for winter over. So once, the planes can go through again, one of the first things will be the disks that have the data. They will be flown, I believe it's up to MIT, is where they're going to then do the processing to add that together and try to do the further results there. So it's a very long process, but it will hopefully be rewarding. I know they also took data for Sagittarius A star, our own galaxy, because I believe the earlier data set was very noisy, so they couldn't quite get that black hole image. So hopefully this year, they'll finally have the data so they can process that.
Gary's hoping that you can tell us a little bit more about your personal journey from being inspired by contact to your position as an astrophysicist today. He's wondering if there were astronomers who mentored you or who nurtured your interest when you were a kid, and he's wondering how your focus evolved from high school to undergraduate to graduate work to today.
Okay, well, I'll try not to go on too long because, of course, I feel like this is a question that's, open to a lot of talk. Yeah, so I never really wanted to be anything else once I read so the book was From the Big Bang to Planet X by Terence Dickinson, because I imagine some of you guys might be familiar with that. And I just grabbed it on the library because I had a very long school bus ride home and I'd always read. And for some reason I wanted to read about astronomy, and that was it. I do remember my dad taking me out to see Hale Bopp in Hayukataki when I was a kid, and that was really cool, but that was a little bit before. And then, yeah, radio astronomy. I was a ham radio operator. I guess I still am. I still have my license, KB3HTS73, in case anybody else is. And I went off to undergrad at Case. I was a physics major. I was the only woman, of course, because that was well, I guess is maybe still a thing, I don't know. So 2004, did my master's at Case as well. I did a lot of traveling in between. I did a lot of backpacking and stuff, so that was pretty fun. And then I actually went to the Netherlands for my PhD, working for a project that didn't really work out. So we were going to, speaking of imaging this guy, we were going to image the entire radio sky. I know firsthand this is very hard and it's not really going to work. So I didn't really work out in Amsterdam, and I actually switched to Toronto and worked with Brian, my PhD supervisor there, who, you know, I definitely somebody who mentored me, and I don't think I'd be an astronomer without him today. And we did a lot of cool explodey things. And yeah, so then basically from that work, I got my thesis, and then I got this job. I started October 2019, so a few months before the pandemic. Then we all went home. I still go in now, but nobody else is there. I just like to sit in a nice quiet place and work. So yeah, astronomers, there was like an astronomer at University of Pittsburgh. I grew up in Pittsburgh who like showed me around and stuff. I did go a couple times to the Pittsburgh Amateur Astronomy Association's meetings. So that was pretty cool. Yeah, working for Jill was very cool. She was definitely, I would say, the most intelligently intimidating person I've ever met. And I don't mean that like as a mean thing. She's just like a very intelligent, very driven person. It was very cool to be, work with her and like just drive around and hear her tell stories about all the things she's done, because she's done a lot of crazy things, and a very formidable woman. Yeah. I guess that's it. Oh, and I've always written. I used to write for like the school paper, and now I get to write for Astronomy Magazine and all those. I actually have to write for any subscribers of Astronomy. I'm writing a tidal disruption event article due next month, so it should be out by the end of the year. So
Very cool. Thanks. So Howard is wondering if you send and receive international Morse code.
I never got into CW, which is what the Morse code is called. I do like know how to do it because you had to do it for the licensing back when I started, because I got my ham radio license when I was like 16 or something. So before I could drive. Never got into the Morse code, unfortunately. Sorry.
Jim is wondering where you go from here. What's next?
Oh. Well, that's a good question. So I am a postdoctoral fellow, which means I am currently in year 2 of a 3-year contract, which I hope will be a 4-year contract, knock on wood. Probably be a 4-year contract. There's a pandemic on, of course. I do like to teach and I do like to write and stuff. So maybe I was thinking more like a liberal arts college professorship than like a really hardcore research stuff, because I like my research, but I also just like to share things that I'm interested in and stuff like that. So I think that would be very nice someday. We'll see. Very competitive. So
Gary's hoping that you'll post the title of the book that inspired you into the chat.
sure, actually. If you guys don't mind, it's right here. So
Oh, there you go. Yeah.
if you can see it. I think it's out of print, but I found a copy of it on Amazon, so I just had to get it. And look, it has a very nice picture of Andromeda on the cover. So what more does a budding astronomer need? And it's definitely out of date now, but I still had fun looking through it. But I could still put it in the chat if you want.
So Jim posted a question, but I'm not quite sure what he's aiming for with the question. If Jim, if you can re-enter that, elaborate on it a little bit.
Yeah, are you finding that always in your profession that you rely on grant funding, going from one to another? Anytime anybody's want to do these kind of studies, you always find yourself always going to rely on grant funding?
Yes. Well, so, okay. The first thing to say is like, I'm not at the stage of my career where it's my own grant funding. It's like the people I work for, their grant funding, which is a slightly different thing. One of the big reasons for, say, space telescopes, and it's good to work on those, is you actually get money if you get time on Hubble or Chandra or any of the big NASA telescopes. So that's deliberately done that way, so you'll have time to then work on your research. So it's roughly, say, for Chandra, $1 a second. So, you know, if you get a 20,000 kilosecond project, well, you know, you can do the math. Radio astronomy, unfortunately, does not do that, which is kind of annoying, but yeah, so it's a lot of grant funding. Like the next stage is I'm definitely gonna be applying for my own. Usually what happens is a university will, pay you because of course they want you to teach and stuff and your grants aren't gonna cover that. So it would be something like we'll pay you for that. And then, you're expected to bring in money to get, say, tenure, or if you have a summer salary, then you're going to get the money yourself for that is usually how that works. And that's usually NASA or National Science Foundation. Sometimes Department of Energy gets involved, usually if it's dark energy, because the word energy is in there. I'm not quite sure why, but very little private money in astronomy.
A lot of competition, in other words.
Yes, that's for sure.
So I think this will be our last question, just to be a little kinder to Yvette, who's talking to us from the East Coast. Howard is wondering if your cross-stitch images are digital or analog.
Well, I guess they're digital because they're pixels. So yeah, but I guess it's at what point do you cross over to analog if it's thread, right? So yeah, this is a question when it's not just after midnight, I think, to think about. But
so thank you very much again for appearing and speaking to us. It was a really fascinating talk, and it was really nice to meet you and have you join us and fill us in.
Thank you all very much. This was really fun. I hope you're all doing well out in Oregon. I hope I can someday visit. So yeah.
Yeah, that would be great.
Yeah, I'll tell you guys about the superluminous supernova if I get that time. So fingers crossed.
Yeah, that would be super cool.
Yeah.
All right.
All right, 7-3. Goodbye.
Thanks again.
Yep.
Take care.
Good night.
Thanks for coming, everybody. Next month is the fabulous astronomy fair. And as Margaret said, it'll be online again, very much like it was last year, where we'll have separate sessions and all sorts of different kinds of talks and things. There should be something for everybody. So please come back then. And thanks for joining us. Have a good night.